Continuing with our review on integration, we're going to see a few more types of situations. Let's say we want to integrate the function root of 1 plus cosine of 4x between 0 and pi over 4. At first glance it looks like there's not a lot we can do. We have a square root of something that has nothing to do with the variable, and therefore it's not clear what to do. Substitution doesn't seem to be an option, because if we were to take 1 plus cosine 4x for a new variable, then the derivative is nowhere to be found. Very often we can transform an expression into something simpler using trig identities whenever the expression contains trig functions. So in this case we have this cosine 4x. One of the most useful trig identities for integration is the double angle formula, namely that cosine of twice an angle is 2 cosine square of that angle minus 1, which can also be written 1 minus 2 sine square of that angle. Of course, there's a counterpart for sine of twice an angle, which is 2 times sine cosine of the angle. So what does that mean in this case? 1 plus cosine 4x, we can interpret 4x as twice an angle for the angle theta equal 2x. So if theta equal 2x, cosine 4x, which is 2 theta, can be replaced by 2 cosine square of 2x minus 1. When I add 1, I get 2 cosine square of 2x. So that's good, because that means that what's under the square root can be interpreted as a square. Namely, we get the integral from 0 to pi over 4 of root of 2 cosine square 2x. Root of a product is product of the roots, as long as both factors are positive. So here it is root 2 times root of cosine square 2x. Root of cosine square 2x is really absolute value of cosine 2x. But because x is between 0 and pi over 4, 2x is between 0 and pi over 2, and that means cosine of 2x is non-negative. Therefore, what we obtain is really a root 2 times cosine of 2x. We can pull out the constant root 2, and we get the integral from 0 to pi over 4 of cosine of 2x. And now we know how to integrate that. We've seen that the integral of cosine kx is 1 over k sine of kx. In this case, k is 2. So we get root of 2 over 2, and then we have to evaluate sine of 2x between 0 and pi over 4. The value at pi over 4, 2 times pi over 4 is pi over 2, sine pi over 2 is 1, so we get 1, and at 0, sine is 0. So we just get square root of 2 over 2. Let's look at another example. This time we want to integrate from 0 to pi square root of 1 minus cosine x. We're in a very similar situation to the previous example. We have this problem of something under a root that we would like to transform, and we have again a trig function. So we can use a trig identity, and we're going to use essentially the same trig identity this time, again the double angle formula for cosine of 2 theta. But this time I would like to transform my 1 minus cosine x into a square, and for that I'm going to interpret cosine x as cosine 2 theta, where theta is x over 2, and replace cosine x by 1 minus 2 sine square of theta, in other words 1 minus 2 sine square of x minus 2. So 1 minus cosine x becomes 1 minus 1 plus 2 sine square of x over 2. So again, we obtain 1 minus cosine x as a square. So that's good. We get the integral from 0 to pi of root of 2 sine square of x over 2. Again, we can write that as square root of 2 times square root of sine square. And square root of sine square is just absolute value of sine of x over 2. And because x is between 0 and pi, x over 2 is between 0 and pi over 2, and therefore the sign is positive, so we can drop the absolute value and we get square root of 2 integral from 0 to pi of sine of x over 2. We know how to integrate something like sine kx. namely integral of sine kx is negative 1 over k cosine of kx up to a constant. And in this case, k is 1/2. So when I take negative 1 over k, it's negative 1 over 1/2, I get negative 2. Therefore, we obtain 2 square root of 2 and negative cosine of x over 2 that we evaluate between 0 and pi. The value at pi is 0 because cosine pi over 2 is 0. And then we subtract the value of negative cosine at 0. So we subtract negative 1, in other words, we add 1. So we get 2 root 2 times 1, which is just 2 root 2. Another kind of situation where there is a standard trick to deal with this type of integral is when we have an improper fraction. What I mean by that is that you have a quotient of two polynomials and the degree of the top is not less than the degree of the bottom. And so in this case we have this 3x squared minus 7x divided by 3x plus 2. There's no clear option for substitution, but each time we have an improper fraction, in other words, degree at the top is higher than, well, is not less than the degree of the bottom, we can transform that into a situation where the degree of the top is less than the degree of the bottom using long division. So let's divide 3x squared minus 7x by 3x plus 2. To start with, we're going to divide 3x squared by 3x, taking the terms of highest degree both in the dividend and divisor. And 3x squared divided by 3x is just x. So here is my x. I multiply x by 3x plus 2 and I write the result below 3x squared minus 7x. So I get 3x squared plus 2x for the product of x and 3x plus 2. And then I subtract this to 3x squared minus 7x. The x squared disappear, that's how we picked x. And then I have negative 7x minus 2x gives me negative 9x. Then we compare the degree of what we've obtained here with the degree of the divisor. Negative 9x is of a degree that is not less than 3x plus 2, so we iterate this process. Namely, I'm going to divide negative 9x by 3x, and that's negative 3. So I put negative 3 here, then multiply negative 3 by 3x plus 2. I get negative 9x minus 6, and subtract this to negative 9x. The x's disappear, and then I have 0 minus negative 6, which gives me positive 6. Now I have obtained something whose degree is less than the degree of the divisor, so it stops. And the interpretation of this long division is that 3x squared minus 7x divided by 3x plus 2 can be rewritten as x minus 3 plus 6 divided by 3x plus 2. Therefore, the integral is really the integral of x minus 3 plus 6 over 3x plus 2, and I can split that into two integrals. The first one is just integrating a polynomial, so there's no problem with that. And in the second one, I'm going to use a substitution where u is 3x plus 2. Well, there is a typo, it should be just u equals 3x plus 2, and therefore du is 3dx. So we're going to replace the 6dx by 2du. And so for the second integral, we get 2du over u. Of course, the integral of x minus 3 is just x squared over 2 minus 3x. The integral of 2 du, I can pull out the constant 2, and then I have integral of du over u, which gives me as an antiderivative 2 natural log of absolute value of u. And u was 3x plus 2, so we obtain x squared over 2 minus 3x plus 2 natural log of absolute value of 3x plus 2 up to a constant. Now another example like that would be the integral of x divided by x plus 1. It's a much simpler example. But again, one of the problem here is that the degree of the top is not less than the degree of the bottom. In fact, they are the same degree. In such a case, of course, we can do long division as well, but we don't really need to write the long division formally. We can do it directly, because when you do long division, you already try to see how many times x plus 1 is in x. So in this case, it's easy to see. You can write x as x plus 1 minus 1, just to make the x plus 1 appear and correct what you have introduced. And now we split the integral. We have x plus 1 over x plus 1 minus 1 over x plus 1. And of course, x plus 1 over x plus 1 is just 1. So now we have the integral of 1 minus 1 over x plus 1. Integral of 1 is x, and integral of 1 over x plus 1 is natural log of absolute value of x plus 1. So that leads us to the next type of standard tricks, which is to split the fraction, which is something that we have used as a step here to essentially do long division without having to write it down. So let's say you want to integrate 3x plus 2 divided by root of 1 minus x squared. In such a case, if we had just 3x over root of 1 minus x squared, we would know what to do, because then you have a composite part which is 1 over root of something. This something is 1 minus x squared. The derivative of this something is negative 2x, so it's a constant multiple of what you have at the top. In that case, substitution should work. On the other hand, if we had just 2 over root of 1 minus x squared, then again we would know what to do, because we know the integral of dx over root of 1 minus x squared, and this is arcsine. So what we do is split the integral in two parts, right? We have 3x divided by root of 1 minus x squared plus 2 divided by root of 1 minus x squared, so we have two different integrals. In the first one, as announced, we're going to use substitution. Using u is 1 minus x squared, then du is negative 2x dx, which means that the x dx inside the integral is going to be replaced by negative 1/2 du. Since we multiply that by 3, we're going to get negative 3/2 integral of du over root u, and then we have twice the integral of dx over root of 1 minus x squared. Antiderivative of 1 over root u, in fact, so this is antiderivative of u to the negative 1/2, so that gives you u to the 1/2 over 1/2, in other words, 2 root u. Since we divide by 2, we end up with negative 3 square root of u plus 2 arcsine of x up to a constant. Substituting back for the value of u, which was 1 minus x squared, we obtain our antiderivative, which is negative 3 root of 1 minus x squared plus 2 arcsine x up to a constant. Now turn to the next video to study integration by parts, which will be the first of a series of integration techniques that we're going to study from now on.